This is the third of 6 videos on discussions related to a permanent magnet DC motor modeling and testing. In this one, we're going to talk about how we run experiments on a permanent magnet DC motor in order to get these model parameters for a torque speed curve, as discussed in the second of these videos. What we want to do is determine the coil resistance, which we can get directly from an ohmmeter right across the motor terminals typically. The other two values we need to come up with, which is the torque constant and also this B sub m, which is an estimate of the rotational damping, and it's a linear coefficient in this assumed case. So what we want to do is run some experiments that can be used to estimate those values. Let's assume that we've determined R sub m, and what we can do then is, I'll just show the summary table and then we'll go through each of these experiments. First I'll explain the data that should be collected. If we're driving this motor, say from a power supply, we can control the input voltage. This is a DC motor, so it's just a DC input. Or we might be measuring the average voltage, the input voltage from pulse width modulation. And so I'm showing this column of data. So we're going to run a series of tests. So the first one is we want to measure the input voltage, just be cap V there. So that can be measured directly. We also need to determine shaft speed for each. So for each test, we're going to be measuring input voltage, shaft speed. Also want to get the motor current, and from these three measurements, 1, 2, 3, we can estimate. Again, this should be capital for voltage in these notes, and then the back EMF can be estimated from Kirchhoff's voltage law. Once we have the resistance and the current, we can estimate the back EMF. And we can fill out this table, and from that table of data, I'm going to show you how we can estimate all these coefficients, right? First of all, measuring current, we can do that a couple different ways. We can, right on the output terminal, we can ground the output, place a multimeter set to measure current, right? In series, on the output side, say, and we can pick up current directly that way. Or you can use a current sensor of some type that might be integrated into a motor drive. Or if you don't have that, you can also, if you don't have also a multimeter and you want to measure voltage instead, and you don't have a multimeter, you can measure current to say. You can put in a series, resistor that does, impact the overall circuit. You have to account for that. But you can measure the voltage just across that resistor, right across the terminal and the ground side of that sensing resistor. Knowing R sub S, you can estimate the armature current, right? And this is V sub S. So different ways that you might measure current. Okay. Remember, when you're running each of these experiments, you're setting the input voltage, measuring speed, either motor, you might be measuring motor speed or output speed. Hopefully you know that gear ratio if you have one. And then you're also measuring current. Okay. Then once you have all that data, then it's several regression analysis correlations to find each of these quantities. If you directly plot the back EMF, which you can calculate again, given the measured input voltage, measured current, known motor resistance, plot V sub m versus the corresponding speed, then you can directly estimate that motor constant, right? Since it's just going to be a direct correlation with that. So takes on several experiments, different input voltages, different speeds, and direct correlation. And you should see that's pretty linear. If it doesn't come out linear, there's something wrong in the assumptions made of the model for the particular motor that you're using. But it should, for most simple, small little motors, permanent magnet DC, that should be a nice linear regression. Now, measurements of the current can also be used with R sub m now. since you've estimated R sub m, now you can take the R sub m multiplied by each of the measured currents from that table, and if you assume that there's no other load in there, then that current is directly responsible for driving whatever internal resistance is in the motor, right? It's running with no external load. So it's working against whatever friction is in the motor. So that tau sub m, if you like, if you plot that versus speed, and if that comes out nice and linear as shown here, then that is a really good way to estimate the internal linear friction. And if you see this nice linear correlation goes through 0, then you're nice and lucky, because it means that that's the only friction. And good motors, maybe that's all they have. They have hardly any other friction, and there's just whatever's due, to internal linear friction. And that's one way to get V sub m. Sometimes you might have some little motors, if you have also gears in there, like the one that we actually use in this lab that I'll be discussing later. There's actually some internal stiction, if you like, and so you might actually see that when you plot the tau sub m, that Rm times Im, it might be offset a little bit, and that's because it's overcoming some maybe internal kind of, let's call it coulombic friction, right? That coulombic friction is basically a constant across all speeds, if a reasonable model of that, and then that is a way to estimate that Coulomb friction as well as V sub m. If you have that, I have a little typo here. There should not be an I in there, right? It should be Vm times omega, right? Okay, but actually then it's also being shifted up because of the Coulomb friction, right? So that's another way to detect if you've got some other kinds of friction models. Again, if this thing is not linear and so on, there might be a better model than just a linear model. That's, again, so now you've determined little r sub m, which is torque constant. You have cap r sub m, which is the internal resistance, and v sub m, you have all the parameters you need for torque speed curve. So now with this equation, have an experimental torque speed curve determined by these coefficients. You can now build this torque speed curve. This doesn't show the gear ratio in there, but you can go back to that other relationship where we derived that if you need it, and insert the gear ratio. It depends again on what you want to plot versus, and also if sometimes you're measuring internal, like in this motors, the encoder. I'll show that in a second in a related video. You're measuring motor speed, not output speed, right? So in any case, you've got enough to estimate your torque speed curve. In the next video, I'm going to talk about experimenting specifically with this little hobby motor that we use for this particular